We're going to learn thin film interference by looking at bubbles and how bubbles work. So if you've ever seen like a bubble, I hope you have. Um, Bubbles are really colorful when you're playing with bubbles. But what's interesting is when they pop, they essentially, like the instant that they pop, they actually show no color. They essentially act like see-through, right? Like it's bubbles are made up of water and soap, so you're just seeing right through them. They're real colorful until they pop, and we're gonna look at why. Why does this happen? And we're gonna explain that with thin film interference and learn what that is along the process. So, sunny day, you're at the park, you want to play with your bubble, so you're gonna blow a bubble, and when you zoom, I guess not really zoom in because this is just a bubble, but it's really made of water, right? It's like a shell of water, and there's soap coating around the outside, and then like kind of like on the inside, right? I don't think. Actually, no, I'll say that thought later in a second. Okay, so now there's a super, 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 super thin coating of soap around this, but this like thick part, that's just and it's once again, it's not really thick. It is thin, right? Like thin film interference, right? The water is really doing the most work here, but the main like thickness comes from the water. The soap is really thin, so essentially what we have is light coming from the sun, right? You're at the park, it's a sunny day. Light coming from the sun, and this is white light, right? So this is white light, and white light is composed up of all colors in the rainbow. And what's going to happen is we have air here, and air has an index of refraction of 1, and we have an index of refraction of around 1 point, I think 4, maybe 3. I'm gonna say 4. I swear I saw 1.33 for water, but we'll just whatever 1.4. Who cares? And then obviously we have air back in here, and that equals 1. All light off of kind of any surface will reflect, right? Like light will naturally reflect off of any surface, even water, right? That's why you can see a reflection on a pond. So some of this light will reflect, and I know this drawing is not going to obey the law of reflection. It's going to look like, the incident angle. It looks wonky. Pretend just because I don't want to move my eye over here, because usually it would like reflect more like up. Just pretend it's gonna reflect that way. Point is, it reflects. Okay, it's gonna reflect, but because water kind of allows light to go through it. It's not a solid. Some of this light's gonna enter in, and it's gonna refract. So it's gonna refract in like so, and we're going to take a look at is what we're going to see is that, well, yeah, now it's going to also reflect off of this kind of contact between the water and the air, right? So it's going to reflect off of here, and it's going to refract back over here. So this is really just optics. This is just what geometric optics tells us. It's that, hey, light will bounce off and refract, and then bounce off and refract, and light will also go through there. That we're not really worried about that. We're worried about what can this eye see. And we in this unit in diffraction interference, we're looking at, well, how does light behave like a wave? Light is a wave. So light might start at a certain like phase, like so, right? I'm not saying in phase or out of phase, right? Because in phase, out of phase, that's between two wave sources. I'm just saying the wave at the sun just starts at a certain like phase. It starts, it looks like that, right? But once the light reflects here, this ray right here is actually going to equal, or not equal, but it's gonna invert. Right? Whatever the phase is here, it's going to kind of invert or look like it's shifted, right? It's really going to invert, flip over. Why is this? Well, if we saw in class, we did a demo. Slinky to the spring, right? The heavy spring. When you got a wave flicking through the heavy spring, right? So if this was my heavy kind of spring, and this is my slinky, when you got a wave through the slinky, what happened was the wave that transmits through the slinky would, continue in this like same, direct, like it'll look like, what you'd expect it to, right? The wave has moved over, but the reflected wave actually looked not inverted, right? Like it looked like, after it changed medium, it just looked like it was going back. Meanwhile, when you had your slinky, the lighter medium, hit this heavy spring, and I know this is hard to see. I know this is hard to see because these markers actually suck. But what we saw was that, the wave, wow, that was actually really nice. The wave actually reflected back. Why is this? Well, when you think about it, at this point, for the heavy spring, the wave that's entering this contact point, the heavy spring is much heavier than the light spring. So that light spring, in comparison, it's movable, right? It's like a free end. It's super light. It can move around. So you can imagine this wave will go up and then kind of shift back and just reflect without inverting. Meanwhile, for the light going into heavy, light as in light, not the thing you see with, but the light slinky, it was so much lighter than the heavy, the spring. This was like the spring at that contact point. It's super heavy to move. It acts like a fixed end, and it causes the slinky to kind of flip over, invert, and reflect back. So, because the index of refraction here is lighter, or allows light to move faster in it compared to the water, it's gonna invert that kind of wave or shift it over. Honestly, I'm like, in terms of like the specifics of what is going on here, I don't understand. Maybe it's quantum mechanics, maybe it's something else. I don't know. But the point is it will kind of follow this kind of model and invert over. So as it passes through the water, it's still gonna be, that same phase that it started here. And when it reflects here, now you're in heavy going to light, right? So it's going to heavy. If you start at heavy going to light, it's just going to reflect back without inverting. You actually stay on the same phase. And same thing when you're passing through, the transmitted wave will always be the same as what was, before, right? Like it'll stay in phase, right? Because it's just passing through. But hey, take a look. This is actually out of phase, okay? We have two waves that are kind of opposite phases. They're out of phase. So if we're gonna see any light at all, right? If we're gonna see any light at all, then what we need is, if this is our starting condition, so if this is, oh my God, these markers suck. If this is my starting condition, my ending condition has to be in phase. Because when you have in phase ending condition, hey, you get constructive interference. And with constructive interference, you can do whatever you want. I don't know why I said that. You can see, right? It's constructively interfering. None of the light's getting canceled out. So remember, if we're starting out of phase, okay, this is kind of backwards, right? Like, if you're memorizing, you're cooked. But if you're not memorizing and you're trying to understand these equations, then this will actually make perfect sense. The path difference for constructive interference in this case is m lambda over 2. Right? So it's going to be m lambda over 2. And it's actually going to be, it's not going to be m lambda over 2. Yeah. It's going to be, we'll leave it as that, and we'll go from there. So it's going to be m lambda over 2. And what is the path difference? Then, well, the path difference is really just the difference of, it's difference of path, right? It's how much distance, what the distance differences of the paths that they travel, right? This wave only travels a certain distance. This wave really travels the same distance plus this distance right here, which is going to be twice the thickness, whatever the thickness is, right? So, right, if this is a thickness T, hopefully it makes sense, right? It has to travel the thickness once, thickness back to get to the original reflected light ray. So, or wave. I want to say wave because, you know, we're dealing with waves here. But change in D is equal to 2T, and hopefully this can kind of help you understand why you only see certain colors sometimes, right? And by the way, I do want to make it clear that this is for like if EC is out of phase, right? This will leads to in phase, right? Because you have those shifts by half a lambda, and that half lambda shift will get them back to in phase. If you have m lambda, just m lambda, right? Just integers, well, now you're not getting that half lambda shift. So if it starts out of phase, it just stays out of phase, right? There's no half lambda shift that gets them back into phase again. So in this case, you can kind of see why you might see certain colors and why you might not see others, right? Because colors are based off frequency, and you get all the frequencies and all the light composed into white light right here. But depending on your wavelength, which is inversely proportional to frequency, right, for the speed of light when it stays constant, then each lambda kind of represents a different kind of frequency. So, or not frequency, sorry, each color has their own lambda. So if, you know, this thickness, if you take twice the thickness and you take a certain, you know, wavelength, and this equation doesn't work out, then you're not going to see that color. If you plug in the wavelength of a certain color and then twice its thickness and do the math, and this equation ends up holding, well, then you're getting destructive interference at the end, because this m lambda is like out of phase to out of phase, right? You don't get that half lambda shift. So that's why you see certain colors. And hey, what happens to bubbles when they're about to pop? When they're about to pop, they have zero thickness essentially, right? Like they're water. You know, you poke a hole and the water's, you know, about to drip, and it has no thickness basically. So when there's no thickness, this becomes zero. So no matter what your color is, right, you just get a path difference of zero, which follows the m lambda scenario. So you're going to get out of phase interference. None of the reflected light is going to hit back to your eye, which makes sense why you don't see any color. At that point, you're not seeing any reflected light because that's all destructively interfering and canceling out. You're seeing all the light that's passing, you know, just through the water, and that's just, you know, from the you just see through it, right? Whatever rocks or trees or whatever, you know, you just see through the bubble. Hopefully that makes sense. You know, thin film interference is pretty cool.